Hey y'all, welcome back. On tonight's homework, we're just practicing a bunch of different limit questions. There's going to be some kind of like what we saw today in class, but a lot of this is just going to be review from earlier in this unit. So the first one gives us a graph, and we can see we have a couple of different discontinuities. We've got a whole or a removable discontinuity going on at 3. We've got this jump discontinuity, which is not removable here at x equals 7, and then we have another discontinuity at 10. So I'm just kind of noticing that before I even jump into the questions. So the first one says, what's the limit as x approaches 10? So as I approach 10 from the left and the right, it is a little ambiguous here, I'll admit, but what we're looking at is what is the y value of that point? So not the one where it's actually defined there, not the one above, but roughly what's this y value? And it looks like it's about a half. So I'm just going to go ahead and call it a half. Letter B says, well, what's the value of the function at 10? So that is where we are going to actually look at this point right here. Where is it actually defined? And it's defined at 1. Letter C says, what's the limit as x approaches 7 from the right? So we do have a discontinuity at 7. It looks like, let me erase some of this clutter here. But as we approach x equals 7 from the right, we can see that we are getting closer and closer to 1. Now, if we approach 7 from the left, the y value is getting closer and closer to 4. And since these two one-sided limits are not equal, we can say that the limit as x approaches 7 does not exist. And if I ever ask you to explain why in this kind of scenario, you would say, well, because the left-hand limit does not equal the right-hand limit. E says, what's the limit as x approaches 3? This is going to be similar to where x is 10. We can see whether we're approaching 3 from the left or the right, the y value is getting closer and closer to 0, even though we never actually get there. There's a little hole there, but that's okay. Remember that the limits don't really care what the value of the function is at that point, just what is the value approaching. Finally, we have the limit as x approaches 0. It appears as though the graph is continuous here, so there's no break or anything, so it's just going to be the value of the function, which is 0. Number 2 says the graph of the function shown below, which of the following statements is false? The first one says the limit as x approaches 2 exists. Now that is true. As I approach from the left and from the right, I can see that on both sides, I'm getting closer and closer to y equals 2. So this is actually a true statement. That's not going to be our answer. B says the limit as x approaches 3 exists. So looking from the left and the right, same reasoning here. The limit as x approaches 3 does exist. That's a true statement. The limit as x approaches 4 exists. This is going to be a false statement. Anytime you have this jump like where the left-hand limit doesn't equal the right-hand limit, that's going to be a false statement. So I'm pretty sure that's going to be my answer. But just to be on the safe side, I'm going to look at the rest of the options. The limit as x approaches 5, we can see from the left and the right. Actually, this is a the graph's actually continuous there, or the function is. So yeah, the limit's definitely going to exist. And E says the function's continuous at x equals 3. Yes, it is continuous at x equals 3. The left and the right-hand limits are the same. We haven't really defined that yet. So kudos to you if you could kind of piece together that, yeah, it is going to be continuous there. Not differentiable, but it is continuous. And we don't really know what that means yet, but we will very, very soon. Number 3, classify the statements as always, sometimes, or never true. The first one says, if the limit as x approaches 3 is 5, then f of 3 has to be 5. Well, that's sometimes true, and I can show you an example of when it could be true or when maybe it's not true. So let's just say, here is a graph, or here are my axes. It says the limit as x approaches 3 is 5. Okay, so I'll just do a horizontal line, like a little constant here at 5. So here's 3, here's 5. Well, if it's just like a horizontal line like this, then this would be true, right? That would be true, that the value of the function is equal to the value of the limit. But if I have a removable discontinuity there, where the limit is still 5, but I have a point defined somewhere else, like by virtue of a piecewise function or something like that, in that case, it could be true. It could be false. Like this is not going to necessarily be true, so we'll go ahead and say sometimes. B says if f of x is continuous, again, we haven't defined continuity yet, but we're getting really, really close to, and hopefully you're already starting to think about what that's going to mean, then the limit as x approaches 7 has to equal 7. Okay, so if 7's out here, continuous, I defined it sort of casually by saying if you can draw the curve without lifting your pen, it's considered continuous. It'll be a lot more precise in a couple of days here. But yeah, then the value of the limit is equal to the value of the function. That's going to be true always. If the limit as x approaches 7 exists, then f of 7 exists. Well, that could be true, but not always. Okay, just like what we saw with letter A, just because the limit exists here doesn't necessarily mean that the function actually is defined there. So if I have a hole here on just some function, right, something that like this, there's nothing to say that it has to be defined somewhere else. It could be, as we've seen, like the piecewise function, like I showed you with part A. So this is going to be another sometimes. Number 4 says let f be a function defined by this piecewise function. And just kind of looking at it really quick, just right off the bat, I'm going to factor this. I'm not even reading the rest of the problem, but I want to go into it already kind of understanding what's happening here. So this is a difference of 2 squares in the numerator. X squared minus 4 is x plus 2 times x minus 2. I'm going to write it like that. And then you can see that at x equals 2, we have a removable discontinuity or a hole. And so basically what this graph is going to look like, it doesn't ask you to sketch it out, but just so you know, it's going to look like y equals x plus 2. It's going to look something like this, right? Y equals x plus 2. But it's going to have a hole at x equals 2, a little hole here. So let me actually erase that. And that hole is going to be defined somewhere else. It says when x is 2, the value of the function is 1. So we have basically something like this going on. The first, and we're trying to say whether or not all these statements are true or false. But hopefully with this picture, it can make it a lot more obvious. So f has a limit as x equals 2. Absolutely, that is true. That is definitely true. The limit on the left side equals the limit on the right side. And actually, we can figure out that point right there. If I substitute 2 in, 2 plus 2 is 4. So this point right here is at 2, 4. Okay, this point right here is at 2, 1. Just to clear that up a little bit, maybe zoom in, you can see that a little better. Clean this up a little bit. B says f is continuous at x equals 2. Well, no, although we don't know the exact definition yet, we did kind of define it by saying that you would need to be able to draw the curve without lifting your pen, and we can see clearly you would have to lift up your pen to jump over that little hole there. C says the limit as x approaches 2 is 1. That is not true. It is going to be 4. Okay, so it's going to be 4. Yeah. You can see that as we approach 2 from the left and we approach 2 from the right, that we are getting closer to 4, not where that extra point is. Letter D says the limit as x approaches 1 is 3. Well, at x equals 1, we don't actually even have a break there, so we're still going to be on that upper section. And you could plug it into the original function. You could also plug it into that simplified line function. Either one will work. You should get the same answer. I'll go with the original one just to be on the safe side, make sure my algebra was good. So I'm going to say 3 squared. Oh, I'm sorry. I'm plugging in 1, not 3. Pardon me. 1 squared minus 4 over 1 minus 2. That's going to give me 1 minus 4 is negative 3, and 1 minus 2 is negative 1. That does equal 3, so that is going to be a true statement. This next section, we're just trying to evaluate limits. We could try to plug in 4 here, but it does make the denominator 0, and it also makes the numerator 0. So this is a case where we have a hole or a removable discontinuity. So let's go ahead and try to factor this first, and hopefully we can get some things to cancel here. We can factor out a 3 as a GCF in the numerator, and the denominator is a difference of 2 squares, so we can factor it as x plus 4 times x minus 4. The x minus 4s will reduce to 1 because we are taking a limit here. We've talked about how you can't just say that those functions are the same because one has a hole and one doesn't. But when we're trying to evaluate the value of the limit at that particular x value, it does not care whether or not the function is defined there. So now we can go ahead and use direct substitution since plugging in 4 is not going to cause any divide by 0 errors. We get 3 over 8, and that's going to be the value of my limit. The next one, we're going to have to use that conjugate strategy that we talked about, not on this notes, but on the previous notes. So I'm going to multiply this fraction by the square root of x plus 3 over itself. That way, really I'm just multiplying this by a fancy form of 1. So this is going to equal the limit as x approaches 6 of, I'm going to leave that numerator factored because I really want to get rid of that x minus 6. And so hopefully the denominator will play nicely here. Usually it does, unless I just mistype something, or maybe there wasn't a hole. Maybe there wasn't a hole to begin with. But no, this is going to work out okay. So let's go ahead and multiply that denominator out. The square root of x plus 3 times itself is just going to be x plus 3. Right? Root x plus 3 times root x plus 3 is going to give me x plus 3. And then if I multiply that root x plus 3 times 3, that's going to be positive root 3 times root x plus 3. And then negative 3 times that root x plus 3 is going to negate that same expression. So those two middle terms are going to add to 0. So that's kind of why we're doing this, is to simplify this and kind of make this work a little nicer. But then we have this negative 3 times positive 3 is going to be negative 9. So I am going to simplify that denominator, leaving the numerator as it is. Trying to get that to be red. Bear with me here. So it's going to be a minus 9 there. So this will equal the limit as x approaches 6 of x minus 6 times the square root of x plus 3 all over x minus 6. Now we can see that we have this same factor in the numerator and denominator, so we can reduce that to 1 safely. That gives us the limit as x approaches 6 of just this expression root x plus 3 plus 3. And so now that we've gotten rid of that expression that's causing the removable discontinuity, we can go ahead and use direct substitution. And we've effectively plugged in that hole, and we get the square root of 6 plus 3 plus 3. So square root of 9 is 3, and 3 plus 3 is 6. All right, C. Looks pretty terrible with all those fractions, but let's see if we can't simplify this. I'm going to multiply this top fraction, this 1 over x, by 2 over 2, and the next fraction by x over x. And the reason why I'm doing this is to find a common denominator so that I can subtract these two fractions. So this is going to equal the limit as x approaches 2 of 2 over 2x minus x over 2x, and all of that over x minus 2. So now that I've got that common denominator of those fractions in the numerator, I can go ahead and combine those two fractions into a single fraction. So this will equal the limit as x approaches 2 of 2 minus x over 2x, all divided by x minus 2. Now, whether or not you have this fraction on the numerator side or the denominator side, you're going to handle the next step pretty much the same way. And that is, whenever you have division, particularly when you're involving fractions, it's often useful to rewrite the division as multiplication of the reciprocal, which is how division is defined in the first place. So I'm going to rewrite this as the limit as x approaches 2 of 2 minus x over 2x times 1 over x minus 2. And I can see that these two factors are very similar, but not exactly the same. They don't cancel out right away, but we could factor out a -1 like a GCF from the numerator to force that factor to be x minus 2. So it will end up looking like this once we kind of put it all together. Limit as x approaches 2 of -1 times x minus 2. That's where I'm getting that from the top. The denominator, I'm just going to multiply the two together, but I'm not actually going to do the multiplication. I'm going to leave the factor separate so that I can cancel the x minus 2's. Now these reduce to 1. And so get this nice little expression, limit as x approaches 2 of -1 over 2x. And now I don't have any problem using direct substitution. So I get the limit as x approaches 2. Oh, actually, nope, I don't want that limit because I'm going to evaluate it at this point. I'm just going to substitute in that 2 for the x and get -1 over 4. Whew, all right, those fraction ones are always kind of a pain, huh? D, the limit as x approaches 0. Okay, so this actually goes back to our very, well, maybe not. Maybe not. This does not go back to the first day. I was thinking that as x approaches infinity, but no. As x approaches 0, you don't see any factors that can cancel here, but that's because 0 is not going to make our denominator 0. I can just safely plug in 0 into x and not have any domain problems, no divide by 0 problems. So I can just straight up use direct substitution to evaluate this limit. Works out pretty nice. So e to the 0 is equal to the same thing, anything to the 0th power is, which is 1. So this is 1 plus 3 over 2, which is 4 divided by 2, or 2. So yeah, always try to plug in that number if you can to use that direct substitution whenever possible. It makes the problem a lot easier. Letter E, now this is kind of what I was thinking about before. This is one of those limits at infinity where we're taking x all the way to the end. Either to positive or negative infinity. In this case, we're taking it to negative infinity, although it ends up not really mattering because this is just a regular old rational function. I'm going to examine the largest degree terms here because I'm only interested in the terms that are growing the fastest. And since we have a 6th degree polynomial on top and a 6th degree polynomial on bottom, the limit as x approaches negative infinity is just going to go to that fraction itself, right? Now the x to the 6ths will reduce, and so this is just going to equal 3/2. That is an ugly infinity. Let me clean that up a little bit. Just really the ratio of the leading coefficients there. That is the, y equals 3/2. That is the equation of the asymptote, the horizontal asymptote. Letter F, we have a nice little piecewise function here, and we want to know what's the limit as x approaches 2, and what's f of 2. So the f of 2, that's kind of a gimme here, because we know what f of 2 is. It's 6. I'm going to just go ahead and say f of 2 is 6 here, just to be done with that one. Now the limit, what we have to do is first we have to make sure that the left-hand limit equals the right-hand limit. So let's find those two limits. The limit as x approaches 2 from the left, that one is going to look at the piece where x is less than 2. So we're going to find the limit as x approaches 2 of this function, and that's going to equal, or actually, you know what? Maybe I'll write it like this, just to kind of simplify this. The limit as x approaches 2 from the left of the overall function is going to equal 3 times 2 minus 5. So that'd be 6 minus 5 is 1. Now let's check the limit on the right-hand side. So on the right-hand side of 2, now we are looking at that bottom piece. This one down here. So let's substitute 2 into there and see where that's headed to. So the limit as x approaches 2 from the right is going to equal 2 squared minus 3. 4 minus 3 is 1. Since these two limits are the same, we can safely say that the limit as x approaches 2 of f of x is 1. And that's because we got the same limit on the left and the right-hand side. And basically what that's saying is that those two pieces are coming together. Okay, they don't actually touch each other because the function is defined elsewhere when x is 2. And if you want to kind of visualize this, if it helps, you can always sketch a graph of this. Looks like this is our last problem anyway. So just for fun, if we want to sketch this out, the first piece is 3x minus 5. That's basically going to do something like this. I mean, this is just a pretty rough sketch, but this is only going to be valid for when x is 2. So I'm going to erase some of that and say, okay, well, here's 2. It's just, like I said, a rough sketch here. Then we have at x equals 2, a point up at 6. So we've got this point up here. And then the last piece is x squared minus 3, which is really just like a parabola, like that does something like this. Okay. But we only want that last section, well, not the last section. We want the section like to the right of 2. So that last piece is going to do something like this, and it is connected there, or not connected is a bad word, but it does approach x equals 2. So I think that's about it for our homework. Let me just zoom out. I think we did all the problems. Yep. So that's it for tonight. Thanks for watching. And if you have any questions or need any help, please reach out. Come see me in the morning or just shoot me an email, and I'll be happy to help you out. Y'all have a great night.